Hey guys, this is Jay, and welcome back to a new video. Here are the concepts we'll be going over today, so let's get right into it. Here we have Clemmensen and Wolff-Kishner reductions, and they're both used to reduce acyl groups into acyl groups, essentially turning the carbonyls into two hydrogens. The top one is Clemmensen, and it uses zinc, mercury, and HCl. And the bottom one is Wolff-Kishner, and it uses H2N and H2, KOH, and heat. We will do a brief recap on EAS, electrophilic aromatic substitution. These reactions add a substituent on the aromatic ring, and these reactions were the ones that we went over in class, including halogenation, nitration, sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. For details and mechanisms on these, make sure to check out the worksheets and the videos from last week. Directing group effect. In electrophilic aromatic substitution, where the new substituent goes on a ring, it's affected by the pre-existing substituents on the ring. If there's an EDG, it activates the ortho and para position, yielding a product in para position and a minor product in ortho position. So here the chlorine is added at the para position. If there's an EWG, it deactivates ortho and para position, making the meta position more favorable. So it yields a product in the meta position. Here, the chlorine is added in the meta position. There's an exception though, and that's the halogens. They're technically deactivating, but because of their lone pairs, they can participate in resonance, and they're ortho and para directing. Here is the chart that Dr. Castleman showed in class. To the left are the EDGs, and to the right are the EWGs. If there are two or more EDG or EWG substituents, then we need to take both of them into account. First, we can't add substituent in a position that is already occupied. If there are two groups, go with the one that is more activating. So here, both ethyl and NH2 are EDGs, and they both favor the para position. But their para positions are different. Since NH2 is more activating than the ethyl group, we would go with the para position in relative to NH2. Here's the practice problem. Finish this reaction scheme. I recommend pausing this video right here. So the first step is acylation. We add an acyl group to the benzene. Doesn't matter where we add it because all the carbons on the benzene ring are equivalent. The second step is bromination. The newly added bromine would go to the meta position because the acyl group is EWG and it favors the meta position. Third step is Clemmensen reaction, which reduces the acyl group into an acyl group. Finally, the fourth step is a nitration step, and it would go to the para position of the acyl group because acyl group is more activating than bromine. We also went over some ways of converting functional groups. One way is Clemmensen and Wolff-Kishner reductions. We can also use iron and HCl to convert NO2 into NH2, and the substituent goes from meta-directing to ortho-para directing. We can also use the Jones reagent to form carboxylic acid. So the substituent can go from ortho-para to meta-directing. Okay, so nucleophilic aromatic substitution. Aromatic rings with strong EWG substituents can participate in substitution reactions. The difference of this and electrophilic aromatic substitution is that in nucleophilic aromatic substitution, the electrophile is the aromatic ring. So here, the OMe attacks the carbon with the leaving group, and it forms the carbanion. Then we use the lone pair of the carbanion to form a pi bond and take off the leaving group, forming a product. We can also do this without EWGs, using NaOH and heat. The negative OH will take the hydrogen, and the CH bond is used to make a pi bond, and the bromine gets kicked off. Then an OH is added onto the carbon as part of the triple bond, and one of the bonds in the triple bond is added onto the carbon, forming a carbanion. And this carbanion finally uses its lone pair to grab a hydrogen from water and neutralize itself and forming a product. And note that this has a benzyne intermediate. This is the Birch reduction. So it reduces the benzene into 1,4-cyclohexadiene. Don't worry about the exact mechanism for this one, just know the general idea. It adds the electron, then it adds the hydrogen, then it adds the electron, then it adds the hydrogen plus. Note that if there are any substituents in the benzene ring, it can affect the outcome of the Birch reduction. So note that the carbanion and the radical carbon are directly across from each other. So that carbanion will form at the carbon attached to the EWG because the EWG can stabilize the negative charge. Thank you guys for watching, and I'll see you guys next time.